Hi everybody, Physics Ninja here, and welcome to my video on Euler Lagrange Equations for beginners. Today what we're going to do is we're going to use this Euler Lagrange formalism here to look at the block on a slope. Now when you're new to this formalism, to this technique to obtain equations of motion, it's always good to go back to something that you know how to solve, for example using Newton's laws, and then compare the results. It's going to provide you with some insight into the new method that you're using. So that's why I picked this problem here. What I also like about this problem is it introduces something called Lagrange multipliers and also this concept of having constraints for the motion, because now my block is constrained to move along this wedge here, or the slope. So before we do that, what I want to do is I first want to solve this problem here just using kind of standard Newton's laws, okay? We're going to start with just a standard approach with a coordinate system that goes down the slope. That's kind of standard textbook formalism. Next thing we're going to do is I want to change the coordinate system, right? Usually you never solve this problem using just the standard XY coordinate system that looks like this, but I want to do it for this problem. And in the last case, what we're going to do is we're going to introduce this concept of Lagrange multipliers, and these are the more generalized equations when you have constrained motion. All right, let's get started. Like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support Physics Ninja. All right, let's go. All right, for approach one is just our standard approach. I'm using the coordinate system that has the x-axis along the ramp. Now, before doing anything, what you want to do is just label all the forces. So in this case here, I have the weight acting down. And what else? There's only one other force in this problem. It's the normal force is acting up. The normal force due to the incline acting on the block. That's it. Now what you have to do is you have to break the forces down into components. And we have two here. So I want to break the weight down into a component here that is perpendicular to the ramp. I call that weight perpendicular. And it's also a component here that is parallel to the ramp. Weight parallel. Now you can draw this vector over here, or oftentimes I just like to draw it right over here. It's the same vector, I'm just drawing it in two different places. Now for the weight parallel, it's simply mg. Now if you think about it, if this is the angle theta down over here of the incline, the angle theta is also the one inside this triangle here. So that means that this vector right here, the magnitude, is mg sine of theta. All right, the perpendicular component then would have to be mg cosine of theta, the way that the angle is defined. All right, we're now in a position to use Newton's laws. So what you want to do is you want to look at Newton's laws in the x direction and also in the y direction. So in the x direction, all we're doing here is we're adding up all of the forces here in the x direction, and we're setting those equal to the mass times the acceleration in the x direction. For the vertical direction here, again, we add up all of the forces here in that perpendicular direction and perpendicular to the slope. And now we're using some of the implied constraint here, because by setting up a coordinate system like this, I know just from common sense that the block is not going to fly off or go into the wedge. So I know that this acceleration here has to be equal to 0. So I just go ahead and I write that statement down, right? So I'm already using the constraint a little bit when I'm writing down this equation. So let's now look at our first one, the sum of the forces along the x direction. There is only one force in the x direction in the absence of friction. So that means that you have mass times acceleration in the x direction must be equal to this parallel component of the weight, mg sine of theta. All right, I'm going to cancel out the mass on both sides. And look what I'm left with. I'm left with an equation for the acceleration in the x direction. It's simply g sine of theta. All right, now go ahead and highlight that case. Now for the y component, again, now you add up the forces in the vertical direction. You have that the normal minus the perpendicular component of the weight. In this case, it's mg cosine of theta equals to 0. So I get one other statement which says that the normal force then must be equal to this value for a block on an incline. Let's go ahead and highlight that one. We'll come back to this case later. All right, so that's it. That's our standard approach. Let's now solve the problem. What if I had just a standard coordinate system that is not that doesn't have one axis here along the incline? All right, the easiest way to get part 2, again, we're just looking for the acceleration, but we want to break it down now into the two components. Well, again, we already solved the magnitude, and we told you that the acceleration, maybe I shouldn't put that on the free body diagram. Let's just draw it over here, right? So we have the acceleration of that object was right here, and the magnitude was g sine theta. Now, all you have to do now is simply break that vector down into the new coordinate system. So this here would have a component here along the new x-axis. And guess what? It would also have a component of the acceleration here along the new y-axis. Okay. Now, if you notice that if this is the angle theta down here of the incline, that means that this here is also the angle theta. So right away, you should be able to write that the components of the acceleration along the new axes, right? These are the new values. You can simply write as a cosine of theta and a sine of theta. Actually, I'm going to put a negative value here because it is pointing down, right? AX is positive, right? But AY should be a negative value with respect if that's the positive y-axis. Now you substitute our value that we had for the magnitude of acceleration. So you get g sine theta, cosine theta. And for this guy here, you get minus little g sine theta squared. Okay, these would be the values of the acceleration now along this new set of axes x and y. Now what you could have done here is you could have also written down Newton's laws along the x and the y direction like this and obtain the same values. Okay, and we could do that in just one step here. So all you have to do here is break the normal force down in this case into a normal along the x direction and a normal along the y direction. All right, if this is the angle theta down here, you should be able to do a little bit of geometry to convince yourself that this is also the angle theta. And right away, you can write that the normal in the x direction is equal to n sine theta. And the normal in the new y direction is the normal cosine theta, where the normal was defined up here. All right, let's go ahead and just substitute that value of n. So what you get here is mg sine theta cos theta for nx, and for ny, you get mg cosine squared of theta. All right, now we simply add the forces. You apply Newton's second law to this problem. You add up all the forces in the x direction. That has to be equal to mass times acceleration in the x direction. Well, guess what? There's only one force along the new x direction. It's simply nx. And nx is right here. So this is mg sine theta cos theta. See, we have mass on both sides. You eliminate that. And lo and behold, we get the exact same value for the acceleration here. G sine theta cos theta is what I had up here. All right, let's just finish this off here. If you do the sum of the forces here along the vertical direction, we have two forces along the vertical direction. That has to be equal to MAY. There's a normal component, the vertical component here, NY. NY was mg cosine squared of theta. And we have simply mg acting down. All right, what you could do here again is factor out mg. And here you're left with cosine squared theta minus 1. And on this side, you're left with MAY. Again, there's mass on both sides. So let's just eliminate it. Now, this looks a little bit different, but I'm going to use this identity here, kind of a famous trigonometric identity here. And you could substitute cos theta, or cos squared theta minus 1, has to be equal to minus sine squared theta. So that's this guy right here. And you can see at the end of the day, my acceleration here in the y direction here has to be equal to the result I just wrote up here, okay? So AY is minus G sine squared theta. These are the components of the acceleration here along the new axes, right? This new x-axis and the new y-axis. All right, so you get the same result as previously. The components end up being different because the component is, the coordinate system is rotated now. All right, let's do a quick review of the approach here for Lagrangian mechanics. The first things first is we're going to define a new function called the Lagrangian. Okay, I'm going to define it with the letter L, and it's pretty straightforward. It's only one equation, and the equation is simply defined as kinetic energy minus the potential energy. That's it. Okay, now potential energy could be gravitational potential energy, could be spring potential energy, depending on the problem, but that is it. Kinetic energy is also pretty easily to define, right? If you're dealing in one-dimensional kinematics, for example, it's just 1/2 mv squared, hasn't changed. So you write that as k minus u, just as an equation. Now note here is that this sign over here is important, okay? The Lagrangians define in terms of the difference between the two. It's not positive. It's not like you're adding kinetic plus potential energy. That would give us the total energy of the system, right? That's not what we want here. We want a different function which uses a negative sign here, and that's the definition right here. Now, once we've defined this Lagrangian right here, what we're going to do is we're going to substitute it into something called the Euler Lagrange and Euler Lagrange equation. Okay, and this is what it looks like. It ends up, you have to take derivatives of this Lagrangian. You have to take derivatives with respect to two variables. First, you take a derivative with respect to the velocity terms. This is this dl over dx dot. There's a dot on top of the x. Whenever you see this for any kind of Lagrange problem, every time you use this dot notation, the dot simply means the derivative of that variable with respect to time, and that's it. Okay. This Euler Lagrange equation also involves taking the partial derivative of this Lagrangian with respect to any position coordinate that you might have here in this definition. You'll see what I mean by this in just a moment. The right-hand side, for this case where there is no constraints of the motion, okay? So this would be like free fall, for example, right? There's no constraints of the motion. In this case, this side of the equation here equals to 0. Okay, so this is the simple case. Now, what happens when the motion is constrained? Okay, what you end up doing here is you use a slightly modified version of this Euler Lagrange equation. Okay, you see here the left-hand side looks exactly like the case I just showed you. Okay, so that hasn't changed. All we do now is you end up defining a function that defines the constraint of the motion. And I'm going to show you what that function is for our case of a block on a slope in a minute. But whatever that function is you set it equal to 0, okay? And once you do that, you end up adding another term here, and this time I'll add it here on the right-hand side of this Euler Lagrange equation. And the extra term is simply taking the derivative of this function right here with respect to any spatial coordinate that you might have in that function. Now there's also this important term right here. This is called a multiplier, a Lagrange multiplier in this case. So what it does is it introduces a new unknown to the problem, but that's okay because you do have this extra equation, and what you end up doing is you end up solving just a slightly more complicated system of equations in order to get the equations of motion. All right, so all of this is in one-dimensional case. Well, our case is actually two dimensions. So how would this formalism here be applied to a 2D problem? Well, it looks like this. For example, we're going to have a kinetic energy. The block slides down like this, right? So our kinetic energy, again, depends on velocity. But if I use a standard coordinate system like this, I'm going to have a velocity that has an x component and a y component. I'm also going to have some gravitational potential energy in the system because as it moves, the height changes, therefore the gravitational potential energy changes. Since my problem will involve both of these coordinates, okay, you end up writing two Euler Lagrange equations. We're going to end up writing one in terms of the variable x and one in terms of the variable y. Okay, and that's it. They look exactly the same as the previous one, right? I'm just substituting x and y values. So this here gives us two equations to solve, but we do have three unknowns. The unknowns for our problem are the acceleration in this x direction, the acceleration in the y direction, and since we have this constraint here, we also have this Lagrange multiplier, which is an unknown to us. So whenever you do any problem with a certain number of unknowns, you always need this many equations. In our case, we have three unknowns. We need three equations. Euler Lagrange will give us two equations. Our third equation comes from the constraint of the problem. Okay? So now let's go to the next page, and what we're going to do now is we're going to start off by writing down what is the Lagrangian for this 2D block. After that, we're going to see how do you write down the proper constraint for this system. And then we simply go through and we're going to construct these three equations and we're going to solve them. That's it. That's all. All right, so we start off by defining the Lagrangian. Our kinetic energy is simply 1/2 mv squared. Now, we know that the velocity is going to be in this direction here. That's our direction. And we can break that down into two components, right? It's going to have an x component using my coordinate system right here, and it's going to have a vertical component, Vy. All right, so you can write this kinetic energy then as 1/2 m. This is Vx squared plus Vy squared. Okay, and now just to kind of clean things up and just to kind of get into this Lagrangian formalism, what I'm going to do is I'm going to introduce these x dot, right? Whenever I have a dot over a variable, it's the derivative of that variable relative to x. Well, that is the variable velocity in the x direction. That's that component. That's the definition of it. So that means that my kinetic energy, you can write it as x dot squared plus y dot squared. That's it. Okay, that's the kinetic energy. The potential energy, well, guess what? It's only gravitational potential energy. What I'm going to do here is I'm going to set the ground right here as y equals to 0. And wherever this block is on the ramp, it's going to be a certain height, y, above the ground, right? So the gravitational potential energy is simply mg multiplied by the height of that object. All right, that's it. Now I just plug everything into my equation for Lagrangian. So this is what it looks like. 1/2 m x dot squared plus y dot squared. And again, I have to take minus our gravitational potential energy, which is mg multiplied by the height. Okay, that's it. That is the Lagrangian for this system. Now let's go ahead and look at the constraint that is imposed when I have a block sliding on a wedge. All right, my goal now is to find the constraint equation so we can then go back and solve the Euler Lagrange equations with a constraint. So again, imagine this block here starts at some initial height h, and then it's going to move down this ramp a certain distance d. Now the angle theta that the ramp makes is constant, right? That doesn't change for this problem. You can define it down here where the incline is, or you can also define it in this triangle up here by the pink angle theta. It's the same angle. Now the motion is constraint because if I tell you what x is, you automatically know how far it went down this y prime value because the angle is fixed. Okay, so that should allow you to write down an equation here. I'll write this one down. Tangent of theta. Again, it's the opposite over the adjacent. So just using those, it's just y prime divided by x. Now my goal is just to eliminate here y prime because I want to have everything in terms of y. And y I had defined it as the height with respect to the ground because this is where I define the potential energy to be 0. So all we have to do in order to do that is just note from this diagram that if I start at some initial height h, this here must be equal to, well, y plus y prime. Okay, so this allows me to eliminate this y prime value from this equation here. So we get y prime is simply that initial value h, some number, minus the variable y. All right, now you go ahead and you substitute that into my value here. So we have h minus y over x. Okay, so this is really the constraint of the motion. However, what we want for the Lagrangian is we want to set whatever this function is, and here it's going to be a value of x and y. We want to set it equal to 0, okay? So that just means you bring everything to the other side. All right, so we're going to work on this equation here and just simplify it a little bit. So first I bring the x over, so I have tangent of theta multiplied by x. All right, and then I bring this numerator over. All I have to do then is just switch the sign. So this becomes plus y minus h. All right, and that here is equal to 0. Okay, and this is my constraint equation for this problem. Okay, so that is what I'm going to be working with here in what precedes. So now let's go look at forming the Euler Lagrange equations using this as our constraint and up here as our Lagrangian. Okay, so we're going to use both of those to get our equations of motion. All right, next step, we substitute things into the Euler Lagrange equations. What we have to do is evaluate these partial derivatives. So let's go look at some of the derivatives that we're interested in. It's the derivative of the Lagrangian relative to x dot. Okay, that's an easy one. X dot only appears in that kinetic energy. If you differentiate with that, you get m x dot. Now, the next thing I want to do with that function here is I want to differentiate it now with respect to time. So if I differentiate this guy here with respect to time, guess what? Mass doesn't change. All you have to do now is put another dot here, right? So that would be the second derivative with respect to time. Now this term should look really, really familiar to you, right? It looks really to me like the mass times the acceleration in the x direction. Remember, acceleration is the second derivative of the position with respect to time. All right, that means that this other term for the y coordinate is going to look very, very similar, right? Because the y dot term only appears in that kinetic energy. All right, let's keep going for our x equation, however. So we need to also evaluate the derivative of this Lagrangian here with respect to the x coordinate. There is no x coordinate anywhere here in this Lagrangian. So that case is easy. It's simply equal to 0. We still have the right-hand side here. All right, so we have this constant lambda, our multiplier, multiplied by the partial derivative of our constraint with respect to x. Here's the constraint equation, so we need to evaluate this. df rather. df dx. Okay. df dx, again, tangent of theta is a constant, so it's simply equal to tangent of theta. Okay, that's it for those three terms. Let's go ahead now and do the same thing now for the y equation, our second equation. So again, our first term here is d dt of the derivative of the Lagrangian with respect to y dot. Okay, again, this term is going to be the mass times the acceleration in the y direction. Y dot dot. Okay, that's it for that term. The next term now is... Now we have to take the derivative of the Lagrangian with respect to the y coordinate. Okay, the y coordinate here appears right here for that potential energy term. All right, so you differentiate that with respect to y, you get minus mg. That's it, just a constant value. All right, we have to worry about taking the derivative now of the constraint relative to that coordinate value. All right, it only appears in this second term right here, and the value here would simply be 1. Okay, now we substitute everything into our Euler Lagrange equations. So let's go ahead and do that. So the first equation here is going to look like this. The first term we had was m x dot dot. Okay, we had minus 0, and this here is equal to this Lagrange multiplier lambda, which I don't know yet. Okay, multiplied by the derivative of df over dx. So that is tangent of theta. All right, we do the second equation now. Second equation is a little bit more complicated, but not too bad. My dot dot, what else? Now it's minus dl over dy. That turns this term here into a positive, right? I'll cancel that negative sign. mg equals to, again, now we have that Lagrange multiplier, the same one, lambda, and multiplied by 1. So that's it for that term. And our last equation here is our constraint equation, which we still have. Okay, the constraint equation is this one. Oops, let's go ahead and change the color again. Now we have tangent of theta multiplied by x plus y minus h equals to 0. Now from this constraint equation, I could differentiate this, right? Not only is x linked to y, but it also means that the velocity in x is going to be linked to y, and also that the acceleration in x is related to the acceleration in y. So what we do is you take the time derivative, the second time derivative of this constraint equation, and we're going to get this expression. Again, tangent of theta is a constant, If I differentiate this with respect to time twice, I get x dot dot. If I differentiate this second term here with respect to time, I get plus y dot dot. And h doesn't change. H is just a number. It's just an initial condition. So that's it, equal to 0. All right, so these are the three equations now that I need to solve in order to get the acceleration and also this lambda values. Three equations, three unknowns. I can do that. Let's go to the next page and finish this. All right, how do I solve this system of equations here? What I'm going to do here is I'm going to substitute everything into my equation here, okay? The first thing I could do is I can eliminate lambda by using my first equation. First equation has lambda, right? So from equation 1, let me just write it down here. From equation 1, you should be able to write that lambda is equal to m x dot dot divided by tangent of theta, okay? And the next thing I want to do here, so you can substitute that right here, m x dot dot divided by tangent of theta. Okay, so we've eliminated lambda from the equations, and we're left with two equations now, right? Equation 2 and equation 3. Okay, so what I want to do now is I want to eliminate x dot dot and have everything only in terms of the y variable. I can do that using equation 3 right here. Okay, from equation 3, what you should be able to write is that x dot dot has to be equal to minus y dot dot, bring that on the other side, and divided by tangent of theta, just the constant. All right, now we're going to go back to equation 2 and rewrite equation 2 here. Work with that equation only. So we have m y dot dot, I don't change that, plus mg, okay, has to be equal to m. I'll just group this term here. This is tangent of theta, okay? And instead of writing x dot dot, I'm going to write this expression, minus y dot dot over another tangent of theta. All right, first we're going to just get rid of the masses. Those appear in all of the terms. Then I'm going to group together all of the y dot dot terms. There's two. There's this one. And then once I bring this to the other side, it becomes plus 1 over. Now this is tangent squared of theta on that side, okay? And here, this here has to be equal to minus little g on this side. All right, now if you just simplify this a little bit, okay? What I'm going to do here, there's many ways to do this. If I write tangent as sine over cos, I should have cos squared of theta over sine squared of theta. And this becomes minus g. What you do now is you multiply through by sine squared of theta. Okay, and what you end up getting here is, so y dot dot, imagine you multiplied all these terms through by sine squared of theta. You'd have sine squared of theta here, plus cosine squared of theta here. It would cross out with this one, and here I'd have minus little g sine squared of theta. Well, this term in the parentheses, that should look like a familiar trigonometric identity. That's simply equal to 1. And lo and behold, look what I have. My final expression for y dot dot, which again is equal to the acceleration in this vertical direction, is equal to minus little g sine squared of theta. This is the exact same result we had in the second approach that we used, right? All right, let's go to the other page and continue the problem. All right, let's find the acceleration in the x direction now. If I know the direction, the y dot dot value, it's very easy to find the acceleration in the x direction. Just substitute into this equation, right? You get minus 1 over tangent theta. And here you just substitute the y dot dot. So this becomes minus little g sine squared of theta. Okay, the negative signs will cancel out. You can rewrite tangent now as sine over cos. And one of the signs are going to vanish, and you're going to be left with g sine theta cosine of theta. Again, that result should look familiar to you. And this is the acceleration in the x direction. Let's go ahead and box that. All right, so what we have here is we have our two expressions that we found using this Lagrangian formalism with the constraint equation kind of built in, right? So that's kind of a nice, powerful technique, right? Because writing the Lagrangian is usually pretty straightforward, right? And then rewriting these three equations here is also not that bad, right? You're just taking partial derivatives and you have to be careful. All of the signs are nicely taken care of, right? When you do this approach, which is what I like. Let's go ahead now and just do a little bit more work, and let's look at what these terms mean, right? What does this term actually signify here in this Euler Lagrange equation? So one last page just to finish off the problem. All right, what I want to do is just provide you with a little bit more insight into both of those terms, right? So remember, in the x direction, we had lambda times df over dx, right? What does that term actually signify? What's its kind of physical meaning over here, right? So that's the goal. So we know we need to find lambda. Lambda I had found from the first equation as being this value here. Well, now that we know both accelerations, you can find what the explicit value of lambda is. It's m over, again, tangent theta. And now I just substitute my x dot dot equation. This is g sine theta cos theta. Okay. Simplify this. Remember, this is sine over cos. So at the end, this is mg cosine squared of theta. That's the actual value of this Lagrange multiplier for this problem. Okay. Remember what my df over dx was. That was easy. That was just tangent of theta. Right, so this first term here, this first term was the multiplication of lambda multiplied by tangent of theta. What does that term mean here for this x equation of motion? Again, just keep substituting things in. There's a lot of these tangent thetas and cos squares, but just be careful. Sine of theta over cos theta. All right, one of the cos leaves. Well, I still have one. Let me be a little bit careful here. I can't get rid of both of them. I can get rid of one. All right, so you're left with this expression right here. So lambda tangent of theta, which is the term that appeared up here in this equation 1, is equal to mg cos theta sine of theta. Okay, let's come back to that in a minute. What about for the y equation? Well, for the y equation, the term was lambda rather, df over dy. What does this term signify? df or dy, that was only one. That was an easy one. So this term just reduced to lambda. So this here was mg cos squared of lambda. Okay, so let's go back to our free body diagram for this problem, right? We did this in problem 2. We wrote that n, which we knew the value, mg cosine of theta. And we had the weight acting down clearly. Just keep that one the same. Now, if you broke that down into components, again, n would have an x component like this, and would have a vertical component like this. If this here was the angle theta, same one as the ramp right here, nx, you would actually be able to see should be the opposite, right? So it would be n mg cosine of theta multiplied by sine of theta, okay? And ny, on the other hand, ny would be the value of n multiplied by cosine of theta. So that's actually what this guy is. This is actually the normal component of the y component of the normal force. And the other term over here is simply the x component of the normal force, right? So this is kind of a clever way here of writing down our equations of motion, right? We should, if we're writing down all the forces, we should have force terms for the normal, right? And that's what these terms actually signify, okay? So they do have some physical meaning to them, and in this case, they represent components of this normal force. All right, I think we've kind of done enough for this problem. Thanks for watching. We'll see you next time.